Hello, everyone, and welcome to Lecture 21 of Computer Architecture. Today, we're going to talk about how to use MIPS in an actual simulator. So we're going to do some examples of programming, writing code in MIPS, and then running that code and seeing the effect of that code. Okay. Last time we talked about floating point instructions. That in the hardware there's a floating point coprocessor that has its own registers, and that this this coprocessor has its own instructions, its floating point instructions that extend the core MIPS ISA. And we said that these instructions only operate on floating point registers, of course, with the exception of the base register, which is an address when you are doing when you're doing load and store instructions. So we looked at the different types of floating point instructions. We saw how we have arithmetic instructions, both single precision and double precision, and the way we write them is add.s, sub.s, add.d, sub.d. And we also saw how we have load and store instructions, and again, we have them for single precision. These are the LW and SW, and then we also have them for double precision. These are LD and SD. We also saw how we have compare instructions, which sets some flag in the coprocessor that is read later on by the branch instructions, which will branch based on whether this flag is true or false. And we also said that there are no immediate instructions. Instead, if we have if we want to have constants in our code, we accomplish that by putting the constants in global memory and loading them from global memory. And with that, we examples of how to write code that uses floating point values. We started with a simple code like this that converts from Fahrenheit to Celsius, and we saw how we use the load and the arithmetic instructions that correspond to the floating point coprocessor. And we also did a bigger example with matrix-matrix multiplication. And this example covered, it reviewed quite a few things of what we did and added some new concepts. We looked at how to generate code for nested loops. We looked at how to generate code for two-dimensional array accesses, and we also looked at how to do loads and stores for double precision values. So this was a brief overview of what we covered last time. Any questions before I start today's material? Okay, if there are no questions, then today we're going to look at how we can use MIPS in an actual simulator in order for us to learn how to write assembly and then run it and observe its results. The simulator that we're going to use is called Mars. So we'll use Mars as a simulator to write and execute MIPS programs directly. And Mars can run on, it's a simulator, which means that it will actually, it's not a real MIPS processor. It's more of a software that simulates a MIPS processor. So even if your processor is not MIPS, which is most likely the case, you can still run the Mars program and use it to run MIPS code and see how it works. And I will make the Mars simulator available on Moodle. It's also available for free online, but for your convenience, I will post it on Moodle so that you guys can use it in the next assignment. Okay, so let's start by writing a simple MIPS program. This is what the Mars simulator interface looks like. Here you just create a new file. You can name it anything you want. And in this file, you can write different programs, and then you can assemble these programs and run them and see how they impact the processor. So here on the right, you can see that there are different registers. So this shows you the contents of all the various register files, as well as the program counter. And there's also the high and low registers, which are used for multiplication, but we didn't really cover that. It's a detail. It's fine if you don't know what these are about. Okay, so let's start by writing a simple MIPS program. And the first MIPS program that we're going to write is just going to subtract two numbers. Okay, so I'm going to write a program that subtracts two numbers, and we'll just observe how the registers are going to change. Okay, so what I want to do is I want to subtract 7 and 5. So the first thing I'm going to do is I want to put 5 and 7 in registers, and then I'm going to subtract one register from the other register. So to put 5 in a register, I'm going to do add immediate. Okay, and notice how when you write an instruction, it kind of shows you suggestions. It tells you, oh, there's an add immediate instruction, there's an add immediate unsigned instruction. So for here, I want to use add immediate, and I'm going to put the result in a saved register. So I'm going to do add immediate S0, and then I'm going to write 0, and I'm going to write 5. So what this does is it's going to put 5 in S0, okay, because it does 0 plus 5, that's 5, and it puts the result in S0. Okay, I'm going to put maybe 7 in another register, so I'm going to add immediate S1, and again, see how it kind of gives you suggestions, tries to guess sometimes what you're trying to do. So here I'm just trying to put 7 in S1, so I'm going to add immediate S1, 0, and 7. So this means S1 equals 0 plus 7. And then I want to do 7 minus 5. So I want to do S1 minus S0, and maybe I'm going to put that in a temporary register. So I'm going to do sub, and I'm going to put the result in T0, and then I'm going to give it S1 and S0. So what this is going to do, this is going to do S1 minus, it's going to do T0 is equal to S1 minus S. Okay? Okay, so this is the we just wrote. First step is to come up here and to assemble this code. So we click this button over here. What that does is it assembles the code for us. So what do I mean by it assembles the code? It takes the code and converts it to machine code that we can run. So one of the nice things about the interface here, it shows you the text segment. So this is where the instructions are. And for each instruction, it shows you the original instruction that you wrote. And it shows you kind of a simplified version of it where you have the human readable names of the value, the numeric, these are the human readable names over here. These are the numeric values. And then finally, it gives you the representation of the instruction as hexadecimal instruction. And it also tells you the address at which at which this instruction was placed in memory. Okay, so add immediate S005. Well, S0 here is register 16, so it shows you that it shows you here that it's register 16. The 0 register is register number 0, so it gives you a 0 over here. 5 over here is just an immediate value, so here it's representing the immediate value as a hexadecimal value. Then it takes this instruction and converts it into the hexadecimal representation of the machine code, right? So if you take this instruction and you convert it into binary, and then take that binary value and express it as hexadecimal, this is what you get over here. Then finally, it tells you that this instruction over here is going to be stored at this address over here. So this address is the beginning of the text segment. And as you would expect, if you look down here, you'll notice that the program counter points to the beginning of the text segment. Okay, if you look at the bottom right, and you look at the registers, the last register, the PC, points to the beginning of the text segment. And what that means is that when we start executing, the first instruction that executes is this add immediate S005. Okay. So now let's execute this code and see what it does. I have two options. I can execute the entire code from beginning to end and see the final result, or I can execute it one instruction at a time using this display over here that has a 1 next to it. So I'm going to execute it one instruction at a time just so that you guys can see the impact of each instruction. So initially, all my registers have 0 inside of them, except of course the global pointer, which points to the beginning of the data segment, and you have the stack pointer, which points to the stack. Okay. So what we'll do is we'll run the first instruction. The first instruction does add immediate S005. So as you would expect, after running the first instruction, S0 becomes 5. Okay, the value of S0 becomes 5, and that is what we see down here. Okay. Next, we're going to run the next instruction. So the next instruction is doing add immediate S107. So we're going to put 7 in S1. So if we press play over here, we see that S1 becomes 7. So now S0 is 5 and S1 is 7. And the final instruction is going to do T0 is equal to S1 minus S0. So we expect T0 to become 2. So here we press play, and you'll see that T0 becomes 2. Okay? So this is how you write code and how you assemble code and how you run code, MIPS code in binary. In Mars. Okay. So does anyone have any questions? I see there's a question in the chat box. Let me read. Okay, so someone is asking, what is the best way to initialize register? Should we use add immediate and one operand being the register 0 and the other operand being the constant 0, or should we use add and add the register 0 twice? It really doesn't matter. Both of them will have the same latency. Okay, so it doesn't matter if you do add immediate register 0 constant 0 or you do add register 0 register 0. Both of them will work and both of them will have the same it will take the same amount of time, and you will see this actually next lecture. We'll start talking about how these instructions are implemented, are executed in hardware. So you'll see how both of them will take the same amount of time. Okay. Okay. So back to our lecture. Here we just did the simple MIPS program. Let's start doing things that are a little bit more complicated. So global variables. When a program runs, obviously it's going to need to access data. It's going to need to get data from somewhere to process it. So one way to do that is through global variables. So MIP-Mars lets you allocate global variables and use them in your program. And the way to do that is as follows. So the MIPS program is divided into two parts, the .data and the .text segments. So what you can do is you can write .data, and then you can allocate global variables, and then you write .text, and then you write your instruction. Okay. Let's do an example of how we load global variables. Okay. Let's go back to our simulator over here. I'm going to go back to the assembly code that I was writing. I don't need this anymore, so I'm going to delete it. So I'm going to have two segments: the .data segment, okay, and the .text segment. So the .data segment is going to include some global variables that I would like to declare, and the .text segment is going to include my actual instruction. Okay. So let me declare some global data. Let's say I want to declare a variable w in global memory, and w for word. So this variable, I need to say what is the type of this variable. So I'm going to say it's word says that w is a 32-bit word. Okay. And then after that I can write what is the initial value of w. So let me just give it some arbitrary value A B C D 1 2 3 4. Okay. So here word is a 32-bit value in global memory, and then I can allocate global variables of different types. So it can be a word. I can also allocate a byte, right? So I can do b dot byte. Okay, and then a byte is going to be 8 bits. So in other words, if I'm going to express in hexadecimal, it's going to be 2 hexadecimal digits. So let me just put FF over here. So FF is essentially all ones. Okay. So now that I have these global variables, the next step is how do I access these global variables? Well, these global variables are going to be put in the data segment in memory. So if I want to access them, I just use load instructions. So I can write LW. Let's say I wanted to load W into some register, maybe T0. So I can write LW, okay, and then I write T0. So I give it where the destination, and then I give it the address. So in this case, what I can do is I can just write W over here. Now, what does this mean? So W, the word W, is going to be in global memory, but while I'm writing the code, I don't know where the assembler is going to put it in global memory. So what the assembler does is it gives me the option of just writing W over here to represent the address of the word W. And then later on, when the assembler assembles this code and puts W at a specific place in global memory, what it will do is it'll replace this W over here with the actual address of W. Okay, and we'll see this when we compile, when we assemble the code. Okay, so this is if I wanted to load W. I can also load B. What instruction do I use to load B? I don't use LW. I'm going to use LB, right? Load byte. So I can do LB, put maybe the result, I'll put it in T1, and I can give it B. This is how we would access a byte from global memory. If you remember, there's two versions of loading a byte. I can load bytes as a signed value, and I can load a byte as an unsigned value. So here, if I load this byte as a signed value, it will interpret these bits as a signed integer. So these are FF, which is 1111111. So that's essentially -1 if you interpret it as a signed integer. So when we load that byte into a 32-bit register, what load byte does is it does signed extension. So it'll fill the remaining the remaining bits with 1. If I wanted to treat it as an unsigned integer, then what I would do is I would use load byte unsigned. So I'd do load byte unsigned. See the difference? I'm going to put this in T2. I'm also going to give it B. Okay, and then if in this case what happens is when we load that byte, which is 8 bits, and put it in a 32-bit register, the remaining bits are going to be filled with 0, not 1, because it's going to be treated as an unsigned value as opposed to a signed value. Okay. All right, let's assemble this code and run it and see how it works. So I'm going to hit assemble over here. And now I get the resulting code. So one thing you'll notice is that LWT0W over here was converted into 2 instructions. Why 2 instructions? Well, the reason we converted to 2 instructions is because W, well, actually, let me explain, before I explain the instructions, let me explain what's going on down here. So this here at the bottom is the data segment. And you'll notice that in the data segment, we have the value that we gave to W over here at offset 0 from the beginning of the data segment. And then the value that we give to the byte over here in the least address byte of the second word in the data segment. Okay. So when I load when I do LWT0 and I give it this address W refers to the address over here, 10010000. So this is a 32-bit address, but we know that we can only provide kind of a base register and an offset, and the offset can only be 16 bits. So we can't just provide a 32-bit address as a parameter, as an operand to the load word instruction. So instead what we do is the assembler breaks this load word instruction into 2 instructions. The first one is load upper immediate. So the load upper immediate instruction will load the upper 2 bytes or the upper 16 bits of the address into a register. In this case, it's loading into register 1, and we'll see what 1 is later on. And then what it does is that the remaining 4 bits, in this case, the remaining 16 bits, in this case, they're just all zeros, but they may not be. The remaining 16 bits will be provided as an offset from the register in which we loaded the upper 16 bits. So this is how we load word from a 32-bit address. We take the upper 16 bits of the 32-bit address and put them in a register, and then we treat that as the base register, and the lower 16 bits of the address are given as an offset to load word. Okay, so this is what is going on over here. What is the register that we're using? This is register 1. So if you look at what register 1 is, it's the register called AT. Now, we haven't seen AT before. This is the first time we're seeing it. And what AT is, it's basically an assembler temporary. So one of the registers in MIPS is reserved for the assembler to use. Why? The reason is that sometimes the assembler will take a certain instruction that you wrote and maybe break it up multiple instructions as it did over here. And to do that, the assembler needs a temporary register to use. So this register AT is reserved for the assembler to use in situations like this. So as a programmer, we don't touch this register. We just let the assembler use it. Okay? Any questions so far? I'm about to run this code and show you what it does. Any questions?
Sir, I have a question.
Yes?
Does that mean when we use the load upper immediate to put an address of a label in a register, we use it just because it's hexadecimal? Because we could have used it, we could have used the add immediate to the 0 register, and we don't have overflow, right?
Okay, so add immediate takes a 16-bit constant. So if I do add immediate to a 16-bit register, that's going to only be able to initialize the register to a 16-bit value. So it's going to initialize the lower 16 bits, and the upper 16 bits are going to remain empty. Okay, But here
okay,
my
16
address
bit.
is a 32-bit value. My address is a 32-bit value. So what I'd like to do is I'd like to initialize all 32 bits, not just the lower 16 bits. So I use load upper immediate to initialize the upper 16 bits. Okay, and then I can use add immediate to initialize the lower 16 bits. Or in this case, because I'm using this as an address to a load instruction, I'm not jumping to it or anything. I can simply use the offset to represent the lower 16 bits.
So here it breaks the 32 bits. And what it does here.
So here what it does is I have a 32-bit address, and I want to load from this 32-bit address. Okay. However, in my load instruction, I can only provide a base register and a 16-bit offset. So since my offset is only 16 bits, what I will do is I will take my 32-bit address and I will break it up into two parts. I will use load upper immediate to initialize the upper 16 bits. And then the lower 16 bits are going to be encoded as the offset from the register where I put the upper 16 bits. Okay.
Oh, okay, thanks.
Yeah. So now when I put the upper 16 bits in register 1, and then I add to it the offset, now I get my full 32 bits. And you can notice that the same thing is applied for load byte and load byte unsigned. In both of these cases, I'm taking the upper 16 bits and I'm using load upper immediate. And then the lower 16 bits, which in this case are going to be 0004 in hexadecimal, these are going to be provided as the offset to my load byte and load byte unsigned instruction. Okay. All right, let's run this code and see what happens. First thing, the first instruction will we'll do load upper immediate. It takes this constant that I provided it with, and it puts it in the upper 16 bits of register 1. So here register 1 is register AT, and you'll notice that now in the upper 16 bits I have 1001. Okay. Next, what I do is I'm going to do load word, and I'm going to provide AT as the base register and 0 as the offset. So that's going to load the value stored at 1001 0000 plus 0, and we'll put that in register 8, which is T0. So when I run the second instruction, you'll notice that T0 now has A, B, C, D, 1, 2, 3, 4, which was the value of W. Okay. And then for the next instruction, same thing. I use load upper immediate to initialize AT to the upper 16 bits of AT. And then I use 4 as an offset. And now, because I'm using load byte unsigned, let's see what happens. So now T1 is going, so the byte that I loaded was FF. So T1 now has FFFFFFF. Why is this the case? Because I treated the byte as a signed integer. So when I loaded an 8-bit signed integer into a 32-bit register, I did sign extension. So since the leftmost bit was 1, I filled the remaining bits with 1. Okay. And then finally, when I did load byte unsigned, I'm going to treat FF as an unsigned value. So in this case, when I do load byte unsigned, what happens is I get 000000FF. And the reason is that FF was treated as an unsigned value. So when I load an 8-bit unsigned integer into a 32-bit register, I fill in the remaining bits with 0. Okay, any questions about this? Is everything clear? Okay, so this was an example of how we can access global memory using in Mars using these labels to our code, to our data, and then using labels inside of the instructions. Okay, so this was the code that we wrote. All the code that I'm going to write will be in the slides, so it's okay if you don't take note of it. And then one of the key things here is that the assembler replaces these labels W and B with the actual addresses loaded, and it uses load upper immediate and the temporary AT register to accomplish this. All right, now let's look at printing. So when we write programs, we don't just write assembly code that, the values that stay in the processor. We are usually interested in printing the results and showing them to the user. And Mars provides us with a way of printing, and this is specific to Mars, by the way. This is not MIPS, what I'm about to explain. This is specific to Mars. So what Mars does, it allows you to call the syscall command. Syscall is basically a system call, so it tells it kind of calls a system function that does something. And the way we determine which function in the system we would like to call, which of these special system functions, is by setting v0. So if I set v0 to 1, for example, and then I call syscall, what happens is I will print an integer. If I set v0 to 4 and I call the syscall command, then I will print a string. Okay, so let me kind of show you an example of how that works. Let's say I wanted to print the number 5. Okay, so I want to print the number 5. What do I do to print the number 5? Let me go back to MIPS over here. So I don't have any global variables, so I'm going to clear my data segment. And in my text segment, I want to print the number 5. So to print the number 5, I'm going to do a syscall, which calls the print function. But before I do that, I need to first pass 5 as an argument to the function that I'm about to call, and I need to tell syscall what the function to call should be, and I do that by setting v0. Okay, so first I'm gonna pass 5 as an argument. Pass arguments to any function. We put that argument in the A register. So I'm gonna do add immediate A0, 0, and 5. So what this does is it's going to put A0, it's going to put 5 in the register A0. Now I want to call my print function. So to do that, I'm going to call syscall. However, before, and you notice here it says syscall issues a system call. But before I call syscall, I need to tell it which system call I'm calling, and I do that by setting v0. So in this case, I want to call the system call that prints an integer. So to do that, I want to initialize v0 as I said over here. I want to set v0 to 1. Okay, and I do that like this. I'm going to do add immediate v0, 0, and 1. So this code over here passes 5 as an argument to a system call and specifies that it wants system call 1 to be called, which prints an integer. So if I assemble this code, okay, so you'll notice over here that each of these instructions has the corresponding numeric values, the actual binary representation, and then the address at which the instruction is located. And if I run this code, we can look over here at the bottom. I'm not going to run it step by step now. You guys have already seen how to run things step by step. So if I run this program, you'll notice that what I get is 5. So here I printed the value 5. Okay. All right. Well, this is interesting. Any questions? Okay. Well, this is interesting. So someone's asking, what if we want to print multiple arguments with syscall? So it depends on the system call you are calling, right? So different system calls take different numbers of arguments. The system call for printing integers takes 1 argument, which is the integer you're printing. So if you want to print multiple integers, you have to call that system call multiple times. And we will actually have an example about that. Okay. All right. So we've seen, so this is the code that we looked at for printing integers. Now let's look at how we print strings. So to print strings, a string is essentially an array of characters, right? A string is an array of characters. So the argument that we want to provide to the system call should be a pointer, an address of the array of characters that we would like to print. Okay, and that the string has to be null terminated. You guys should be familiar with null terminated strings from previous courses. The string has to be null terminated. So let's see how we can do that. Let's see how we can print a string. Here. And this time what I will do is I'm going to put the string that I want to print in the global data segment. And we do that as follows. So I have my string, I'm going to name it message. Okay. And I want to say that message is an array of characters. So that I'll do that like this. All right, ASCII. But you notice there's two versions of ASCII. There's ASCII and ASCII-Z. ASCII it has an array of characters that is not null terminated, whereas ASCII-Z has an array of characters that is null terminated. So in my case, I want to print the string, so I'm going to provide a null terminated string so that the print function knows where to stop. Okay. So here I write ASCII-Z, and now I can give it its value. So I can write anything over here. I'm just going to write hello world. Okay. Okay, so now I have this message, the string in global memory that I would like to print. The next step is to call my system call to print this string. Okay, so first of all, rather as you saw in the previous slide, so the code for print string is 4, not 1. So in my code over here for 0, I'm going to provide it with 4, not 1. So 4 will make sure that we interpret the argument as a string and print it. As for A0, now what I would like to put in A0 is the address of message. Okay, I want to pass the address of message. And the way that we do that is we have a special pseudo instruction, a load address. So load address called LA, load address. This is not an actual MIPS instruction. This is an instruction that's provided by Mars. Okay, so Mars provides us with this instruction, and the assembler converts this instruction into actual MIPS instruction. So here what we do is we do load address. Okay, we will first in A0, so we're going to put A0 over here, and we're just going to provide message. And what the assembler will do is it will take load address and it will convert it into code that stores the address of message in the register A0. Okay, so as you can probably figure out, what is it going to use? It's going to use load upper immediate and or immediate. Okay, so let's assemble this code. So we're going to assemble this code. Okay, oops. Oh, I have a typo over here. This should be MSG. Okay, now let's assemble this code. Load address A0 message. So first of all, the address of message is the beginning of the data segment 100100000. So to get that, we're going to do it converts the load address instruction into load upper immediate and or immediate, which we saw before, as a way of storing a 32-bit constant, a 32-bit address inside of a register. So now what we're going to do with this 32-bit constant is we're going to pass it as an argument to our system call, and then add v0 tells it what system call to call, and then system call calls the actual system call. So if I run this, as you would expect, what it does is it prints hello world to the terminal. Okay, and I have a typo in how I wrote hello world. Let me go back. Okay, so I misspelled hello world over here, so it's not supposed to have a W here. So let me run that. And you'll notice that I have hello world in my output. Okay, any questions about printing integers and strings? So that's correct. Null terminated strings will end in with \0. That's correct. Okay, so let's do a slightly more complicated example. So let's say I wanted, so this is our example of printing a string, and like we saw before, this message is going to be, the assembler is going to replace this message with an address that's loaded from register using load upper immediate or immediate, and it uses the AT register intermediate. Okay. Now let's say we wanted to write a loop. Okay, so we want to write a loop that prints a number sequence. So let me write a loop that prints the numbers from 0 to 9. Okay. How do we do that? But let's go to our simulator. Okay, I'm going to click here. I don't need any global variables. And I'm going to write my instructions in the text segment over here. So what I'm going to do, I want to initialize some saved variable to 0, and then keep incrementing it until it gets to 10. And every loop iteration, I want to print that loop index. Okay, so I'm going to print the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, how do I do that? Well, first of all, I'm going to initialize my loop index. So I can write add immediate S0 0, 0. Okay, so what this does is it initializes S0 to 0. Okay? All right, the next thing that we do is we are going to begin the loop. So what does the loop do? It's going to check if S0 is less than 10. If S0 is less than 10, it's going to go into the loop and print S0. Otherwise, if S0 becomes 10, it's going to exit. So how do I check if S0 is less than 10? I'm going to use set on less than immediate. Okay. And then the two instructions that I'm comparing, well, the result is going to go in T0, and the two values that I'm comparing are S0 and 10. Okay. So now T0 will be 1 if S0 is less than 10. So if T0 is 1, I want to go into the loop. If T0 is 0, I want to exit. So what I'm going to use, I'm going to use branch if equal. I'm going to do branch if equal S0, 0. And if they're equal, I'm going to exit the loop. So I'm going to have a label exit. So I'm going to just write exit over here. And later on, I will just have a label exit. Okay? Okay, so if S0 is not less than 10, I'm going to exit the loop. If it is less than 10, I'm going to go into the loop. So in the loop now, what do I want to do? Well, what I want to do is I want to print S0. Okay? How do I print S0? Well, I'm going to use the syscall command, and I'm going to provide it with an argument, which is the value of S0. Now, the argument should be in the A0 register, so what I will do is I need to move S0 to A0. So I do that like this. I'm going to do add A0, S0, and 0. Okay. So now I have S0 and A0. Next, I want to do the system call. So next, I'm going to do syscall. However, I need to tell you what call to make, and I do that by setting V0. So I'm going to do add immediate V0, 0. And if you remember, the code for the system call that prints an integer is 1. Okay. So now I do the system call. So this is going to print S0. Next, what I want to do is I'm going to increment S0 and then go back to the beginning of the loop. So I'm going to do add immediate S0, then S0 and 1. Okay. And then after that, what I will do is I will go back to the loop. So which instruction is the loop condition? The instruction that's the loop condition is the set on less than over here. Okay, so I'm gonna write jump loop. Okay, and then over here I will have a loop label that points to where I want to jump back. Okay, so this is the code for writing a loop that loops over, increments S0 and prints it every time until we get to S0 equals 10. Any questions about this code before I run it? Okay, so let's assemble this code. So I'm going to assemble. As you see, we get all these instructions, and you'll notice how with branch on equal, notice what is the how is exit represented? Exit is represented as the value of 5. Why 5? Because if you go to PC plus 4, you need 1, 2, 3, 4, 5 instructions to get to where the exit label is. Okay, and if you notice with jump loop, the way that's represented in binary is as 100001. Why? Because the label that we're jumping to is 10 less than, which is 400004. So if you divide that by 4, you get 100001. Okay. So this kind of should remind you of how we were converting these labels into values that we store using PC relative addressing or pseudo-direct jump addressing. Okay, so I will run this code. So there seems to be a problem. The values were not printed. Let's see what the problem was. Okay, so the problem here is that I was supposed to compare T0 here, not S0. So T0 is what holds the condition. So I'm supposed to compare T0 to 0. Otherwise, S0 will always be equal to 0 and will exit. Let me assemble that again. Let me run it, and you'll see that the output was 0, 1, 2, 3, 4, 5, 6, 7. Okay, any questions about this code? Everything's clear? All right, so let's do one more example. Okay, let's do one more example. And the final example, by the way, this code that we just wrote, again, the assembler replaces the exit label with 5 and the loop label with using pseudo-direct jump addressing. Now what I want to do is I want to print elements of an array. So rather than looping over an index and printing that index, what I want to do is I want to have an array, and I want to print the element inside of that array. Okay, let's do that. Let's declare an array in global. Okay, so here I'm just in global memory. I'm going to have an array. Okay, let me declare it just for fun. Let me byte. Okay, and the bytes are going to be 2, 4, 6, 8. Okay, so I have an array of 4 bytes. So now I'm going to use this. I'm going to reuse this code. I'm not going to write it from scratch. So I'm going to have a loop. S0 is going to be my loop index. The array size is 4, so here I'm going to have 4 instead of 10 as the loop bound. Okay, and then in every iteration, and we're going to do the same thing once we're going to branch if equals 0 to the exit. Otherwise, we're going to go into the loop. And the only difference is that rather than putting S0 as the argument of our system call, instead we're going to load the byte from the array and give that as the argument to our system. Okay, so how do we do that? Well, I want to use the array. The address of array is array. Okay, so I'm going to clear this. And now what I want to do is I want to load the byte and put it in A0. So to load the byte, I need to have the address of the byte. The address of the byte is going to be the array, the base address of the array, plus the index, which is S0. Okay, so I'm going to first start by loading the address. We had the load address instruction. This is a pseudo instruction again. It's something that MIPS provides us with. It's not an actual MIPS instruction. That Mars provides us with. It's not an actual MIPS instruction. So we do load address, and we can put this address in T0. Okay, over here we're just going to provide array. So what this does is it'll convert it into 2 instructions that take the value of the address array and puts it in T0. Okay, now that I have the address, I want to increment the address by the offset. So I'm going to write add T0, T0, S0. So now I add the index of the loop, which is S0, to the base address. So now in T0, I have array plus the loop index. So now I'm going to load the value at this address as into the argument. I'm going to do load byte. Okay. Put the result in A0, and I'm going to load from 0 of T0. Okay. So now I have code that will loop over this array, and then these 3 instructions here are the only thing that change. Essentially, what we're doing is we are loading from an array at a specific index and providing that as the argument for the print instruction. Okay, so let me assemble that. Okay. So now we have the code. Again, you'll notice how LA was converted into two instructions: load immediate and or immediate, load upper immediate and or immediate. Okay, and then finally, after we're done assembling, we can run. So I'm going to run this code. And you'll notice how after I run this code, oops, nope, that's not what I wanted. Maybe I was safe. And I'm going to run. Oh, okay, no, this was the old output. The new output is down here, and you'll notice that I get 2, 4, 6, 8, which were the contents of my array. Okay, so that is an example of how we can read from an array and print the results of an array to the output. All right, any questions about this? Any questions about how this was the code that we just wrote? Any questions? So someone's asking why we're not accessing the array elements by doing array plus 4 times S0. And the reason we're not doing that is because this is an array of bytes. Okay, this is an array of bytes. The size of every element is 1 byte. This is why we're doing array plus S0 as opposed to array plus 4 times. Okay. Someone's asking what the 0x notation means. We write whenever you see a 0x, this means that the value is a hexadecimal value. Okay, this is just a notation for hexadecimal. If we write 0b, then this would be a binary value. Other questions? Okay, well, if there are no more questions, then we are done with part 2 of the course. This is the end of part 2 of the course. We're done talking about instruction set architecture. We're done talking about how the instructions that run on the processor. And next time we will start with my favorite part of the course, which is part 3, where we're going to put together what we learned about logic design and what we learned about instructions to build a processor that will execute these instructions in hardware. Okay, that is all for today, and I will see you next time. Bye, everyone.